Okay, so like I said, we're starting with the geographical coordinates. First off, latitude and longitude. They are our measurements of geographical coordinates. Latitude lines run from east to west, so they are horizontal. Sometimes people are remember this as lines of latitude are kind of like rungs of a ladder. Longitude lines, the long ones are the opposite, and they run from north to south. And I've also got the coordinates for Grand Ledge up there, 43 degrees north, 85 degrees west when you round it. And that's going to be important because a lot of the things on the celestial sphere and with regards to using sky maps depend on what your coordinates are, particularly what your latitude is. Now, the actual coordinates of Grand Ledge are 42 degrees north, 44 minutes, 35 seconds, and 84 degrees west, 45 minutes, 3 seconds. We're going to make our life easy and use the rounded ones primarily. I actually included this picture because this is hanging in my kitchen at my house. When I lived in the Thumb as kind of a funny Christmas gift one year, my sister made me the plaque with Grand Ledge and its coordinates on it because she said then I would, if I ever got lost, I could find my way home. So now it hangs in my kitchen with the coordinates on it. So next up, we have our diagram. And so this is where we're going to mark the main latitude and longitude points on the globe, as well as what their degrees are. And this is going to be the majority of the latitude and longitude quiz. So if you've got a handle on this diagram, you're going to be fine on that. All right, so let's start with the main reference point, the line across the middle of the globe. Does anybody remember what we call that?
Equator.
The equator. The equator, and the equator is defined as 0 degrees longitude. Or 0 degrees latitude, I'm sorry, latitude. And all other latitudes are measured degrees north or south of the equator. Does anybody have any ideas what these dotted lines would be? Okay, these ones are usually less known. These are the tropics. So the northern one is called the Tropic of Cancer, named after the crab constellation. So Tropic of Cancer. And the Tropic of Cancer is located at 23.5 degrees north. Or yeah, 23.5? Yeah, 23.5. The southern tropic is known as the Tropic of Capricorn, after the constellation Capricorn, which is like if you picture in your head a goat mermaid, like half goat, half fish, that's Capricorn. And the Tropic of Capricorn is located at 23.5 degrees south latitude. And what would be our point at the very top of our globe? The North Pole. Yes, not a trick question, I promise. This is the North Pole. And the North Pole is located at 90 degrees north latitude. Because if you drew a line up to the North Pole from the equator, that would make a 90-degree angle. Likewise, at the very bottom of the globe, we have the South Pole, which is at 90 degrees south latitude. Anybody think they know what this latitude near the North Pole would be? Yeah.
Arctic Circle.
It is indeed the Arctic Circle. And the Arctic Circle is located at 66.5 degrees north. Which makes our latitude down here at the bottom, the Antarctic Circle. Which is of course located at 66.5 degrees south latitude. Now, and this is the unique thing about latitudes, is all of our main latitude markings on the globe are directly related to physical things. Like the equator is the literal middle of the earth. The tropics mark specific places with regards to equinoxes and solstices. You know, the Arctic and the Antarctic Circle are directly related to places that will receive either 24 hours of daylight or 24 hours of darkness at certain times of the year. Longitude lines are different. Longitude lines don't correspond to these very strong, physical things. We kind of just picked the one we wanted to be 0. So this solid line on your diagram, that is what we call the prime meridian, 0 degrees longitude. Do you guys read that green okay, or is that too light? Okay. But yeah, that's the prime meridian, 0 degrees longitude. And there's not, and like I said, there's nothing special about the prime meridian that would make us define it particularly as 0 degrees longitude. It was just arbitrarily chosen. On the other side of the world, where we have this dotted line marked on your diagram, this represents 180 degrees longitude, so the exact opposite from the prime meridian, which is the international date line. So the international date line, a lot of times just abbreviated as IDL, is 180 degrees longitude. And so these are all of the big main kind of defining geographical coordinates. So the next thing we want to do is talk about equinoxes and solstices. Does anybody know what an equinox is, other than a car? Okay. What about solstices? Does anybody know what happens on the winter or summer solstice? Okay. Well, it all has to do with the length of day and night. On the equinoxes, we have equal length day and night. So the vernal equinox, also called the spring equinox, occurs around March 21st every year. And on that day, you will experience an equal length day and night, and the sun's rays shine directly on the equator. So if you were standing on the equator at the vernal equinox at noon, the sun would be absolutely directly over your head. Equinox, sun shines on the equator, equal length day and night. Next is the summer solstice. Again, usually occurs around June 21st. And on the summer solstice, we have our longest day of the year and the shortest night. And the sun shines directly on the Tropic of Cancer, which is 23.5 degrees north latitude. And then, of course, as summer passes, that brings us to the autumn equinox. Again, equal length day and night on the autumn equinox. It occurs around September 21st every year. And once again, the sun's rays will be shining directly on the equator, 0 degrees latitude. And then, of course, there's the winter solstice, which is kind of like the opposite of the summer solstice. On the winter solstice, we have our shortest day of the year and the longest night. And it usually occurs around December 21st every year. And at the winter solstice, the sun will shine directly on the Tropic of Capricorn, or 23.5 degrees south latitude. So what the equinoxes and solstices are really showing us is seasonal changes, why our seasons change. And it all has to do with the tilt of the earth. A lot of times people think that the seasons deal with how close the earth is to the sun, but it doesn't. It all has to do with the tilt. And you can even see it here in this diagram. At the summer solstice, notice the northern hemisphere of the earth is tilted towards the sun. That's why we experience summer in June and July. At the winter solstice, we can see that the southern hemisphere is what is pointed towards the sun, which is why we experience winter in December. But if you were in Australia, you would be experiencing summer in December because they are in the southern hemisphere. And around these times is also where you'll see areas on Earth, the Arctic and Antarctic circles, that have 24 hours of daylight or 24 hours of night. So in the summertime, the Arctic Circle is so tilted towards the sun that the sun never dips below the horizon if you are above the Arctic Circle. And so you literally experience 24 hours of daylight.
How long?
I'm not sure for how long, but it's definitely like at least a month or so.
Okay.
But I'd have to look that up. Likewise, in the winter, the Arctic Circle is completely pointed away from the sun, and the sun will never rise above the horizon. And you get 24 hours of darkness. And I'll show you guys a simulation that kind of shows you how the sun's rays change with their angles a little bit too. But seasons have everything to do with the tilt of the Earth. So we can get it written down. On the equinox, the sun shines directly on the equator. Equinox, equator. And an equinox means equal length day and night. So this should be the easy one to remember because equinox, equator, equal length day and night. They all start with that EQ. Equinox, equator, equal length day and night. The winter solstice, once again, is our shortest day of the year and the longest night, where the summer solstice is the opposite. The summer solstice is our longest day and the shortest night of the year. So currently we have passed the vernal equinox and we are heading towards the summer solstice. So that's why it's being light out later and later every night, is because as we head from the spring equinox to the summer solstice, our days are getting longer and longer. Now I'd like you guys to include this diagram in your notes as well. It's another way to help us keep track of sun position. I'll draw another copy of it over here if you want to see how I draw it. But basically, I start with my axes. In the middle is 0 degrees latitude. Up here is 23.5 degrees north, Tropic of Cancer. And then down here is 23.5 degrees south, the Tropic of Capricorn. And then along the bottom, I just marked the dates for the equinoxes and solstices. So starting with September 21st, the fall equinox. And then December 21st for the winter solstice. And then March 21st for the vernal equinox. And then June 21st for the summer solstice. And then again at the end, we come back to September 21st, the fall equinox. And then we just mark the sun's position at each of those. So again, at the fall equinox, the sun shines directly on the equator. At the winter solstice, the sun shines directly on the Tropic of Capricorn, 23.5 degrees south. At the spring equinox, we are back to the sun shining directly on the equator. Then at the summer solstice, the sun shines directly on the Tropic of Cancer, 23.5 degrees north. And then again, when we come back to the fall equinox, the sun shines directly on the equator. And you get kind of a sine wave shape. All right, so now I'm going to pull up one of those simulations that I was talking about. All right, so now we're going to talk more specifically about the celestial sphere. So first off, the first part of the celestial sphere that is important to remember is that anytime we're talking about the horizon in astronomy, we mean the astronomical horizon. And the astronomical horizon is the literal point where the Earth and sky meet. However, we almost never see the astronomical horizon. What we usually see is the visible horizon. And that's because the exact point where Earth and sky meet are almost always blocked by buildings, trees, you name it. Now, if you've ever been out in a very large body of water, like maybe the middle of one of the Great Lakes or the ocean, then you could observe the astronomical horizon as long as you had clear weather. Because when you're on a large body of water, there's not usually anything that's going to obstruct your view of where Earth and sky meet. Now, another thing to remember about the celestial sphere is that the celestial sphere is us kind of taking Earth's geographical coordinate system and projecting it outward onto the sky. And so you kind of get this sphere like grid that all the stars lie on. It's important to remember that the celestial sphere isn't a real thing. Like we all know there's no sphere of stars around us. You know, the stars are all spread out, right? But the celestial sphere is a useful model because it can help us easily locate different stars and constellations and objects. So it's not a real thing, but it is a useful model. We'll start with the basic but most important points on the celestial sphere. Number one is the zenith. The zenith is the point directly overhead. And it does not depend on the observer's latitude. So it doesn't matter what latitude you're at, your zenith is always going to be directly above you. The opposite point of the zenith is called the nadir. The nadir is the point directly under your feet. Once again, it's not dependent on the observer's latitude. Alrighty, folks, I want you to take a moment. Look directly over your head right now. Look up. That is your zenith. Look down at your feet. That is the nadir. That is how you find those 2 points no matter where you are in the world. Zenith is always way at the top, right above you. Nadir is always directly below you. Remembering what the zenith is going to be important especially when we start talking about how to use sky maps, because they are orientated around the zenith. Next up, we have the cardinal points around the horizon: north, east, south, and west. These are another important part of orientating yourself so that you can find specific objects in the sky. Which brings us to the question, how do we find the cardinal points? What are some ways we could find north, south, east, and west? Yes. Using the sun, right? We know that the sun rises in the east and sets in the west. Sun position. How else might we locate the cardinal points? Yes. With a compass, right? You could use a compass. Yes. A map. You could use a map if you know where you are and where you are in relationship with other landmarks. Other thoughts? Right, specifically if it's nighttime, you could find the North Star to locate north. And those are kind of the main ones. Again, when it comes to maps and landmarks, if you know the directions of certain roads, that can also help you. For example, Saginaw Highway runs almost perfectly east-west. So if you know where you are in relation to Saginaw Highway, you can orientate yourself. Additionally, interstate highways, even numbered interstate highways run east to west. Odd numbered interstates run north-south. For example, I-75 runs north and south. I-96 runs east-west. That's why you can take it to get to Grand Rapids. Whereas I-75 is what you'll probably take if you're on your way to the UP. So there's a variety of ways to orientate yourself. All right. Also, because Earth rotates from west to east, all the objects in the sky appear to move in the opposite direction, from east to west. So the reason why we always think of the sun as rising in the east and setting in the west is really just because the Earth is rotating in the opposite direction. Because all of the movement of things that we see in the sky, for the most part, is not related to those objects moving. It's almost entirely related to us moving, the Earth moving. You know, there's a slight asterisk with that because the moon and the planets do also move with respect to us. But everything else is not moving. And so because we observe things as they appear to move around us, you can think of objects in the sky as tracing out circular paths kind of around the Earth, or circular paths around the celestial sphere. And we call those diurnal circles. A diurnal circle is just the path an object traces out in the sky in one day. Now let's talk about the celestial poles. The celestial poles are another important feature of the celestial sphere because again, it helps us with orientating ourselves to find specific objects. The North Celestial Pole, abbreviated as the NCP, and the South Celestial Pole, abbreviated as the SCP, are the ends of this imaginary axis that runs through an observer, and all of the objects in the sky appear to rotate around this imaginary axis. And conveniently for us, Polaris, the North Star, is very, very close to the NCP. That's why it's called the North Star. Interestingly enough, this is pure coincidence. The fact that we have a North Celestial Pole star is pure coincidence right now. The Southern Hemisphere does not have a pole star. There is no South Star. Now, what a lot of people in the Southern Hemisphere have traditionally used for orientating is an asterism, which is like a smaller version of a constellation. An asterism called the Southern Cross, because it's kind of a cross-like shaped arrangement of stars that points toward the SCP, or South Celestial Pole. Now we're going to label the diagram. Oh, oops, I forgot about this part. The NCP is going to be equal to the latitude of the observer, as long as you're in the Northern Hemisphere. If you're in the Southern Hemisphere, your latitude is equal to the SCP. So the NCP is directly above the North Pole. And because the angle that it makes with the horizon is equal to our latitude, for us, we should be able to find the NCP and Polaris, our pole star, about 43 degrees above the horizon in the north. Now we're going to label our diagram. So you should have this same like little picture in your notes. These two circles, the top and bottom, they're just examples of diurnal circles, the path that objects trace along the celestial sphere in one day. And then the point at the top is, of course, our North Celestial Pole. And the point at the bottom is the South Celestial Pole. All right. Another important marker on the celestial sphere is what we call the astronomical meridian. The astronomical meridian is a circle that passes through south, the zenith, the NCP, north, and the nadir. So it's going to be perpendicular to the celestial equator, which we'll talk about in a minute. But it should be a circle that kind of runs like this: north, NCP, zenith, south, and nadir. And the astronomical meridian is important because when objects pass the astronomical meridian, they are at their highest point in the sky. So an object will never get higher in the sky than when it is on the astronomical meridian. The astronomical meridian is often divided into upper and lower meridian. The upper meridian is just the part that is above the horizon that we can observe. And the lower meridian is the half of the circle that is below the horizon that we do not observe. But the astronomical meridian is important because when an object crosses the astronomical meridian, that is the highest it will ever get in the sky. All right, so we're going to kind of label. You should have this little drawing kind of printed on your paper. I think you guys have the east and west points already labeled on it. Label the south and the north points as well. And then label the top up here, the zenith. So remember, the astronomical meridian is a circle that goes through north, south, zenith, and nadir. So this line right here represents the astronomical meridian because it's going through north, south, zenith, nadir, and NCP, they said. Yeah. Next up is the celestial equator. The celestial equator is going to be perpendicular to the astronomical meridian, just like how the prime meridian is perpendicular to the equator on the Earth. And the celestial equator is the diurnal circle that passes through east and west. And the angle that it makes with the horizon is always 90 minus the observer's latitude. So the celestial equator does depend on what latitude you're at. So 90 minus latitude equals celestial equator. So in our case, right, our latitude is 43 degrees. So what angle above the horizon would we expect to find the celestial equator at? $90 minus 43 would give us what? 47. The celestial equator for us should be about 47 degrees above the south horizon. So the celestial equator, 47 degrees above the south horizon for us. So that means some interesting things. Think about if you were standing on the equator, right? The equator is 0 degrees latitude. That means the celestial equator would be at the zenith. It would be directly over your head because 90 minus 0 would be 90. Likewise, if you were at the north or the south pole, right, 90 degrees north or south, the celestial equator would be exactly at the horizon. Another thing to remember is that all stars will move parallel to the celestial equator. All diurnal circles are parallel to the celestial equator. Just like all lines of latitude on the Earth are parallel to the equator. And again, the angle that these stars and their diurnal circles make with the horizon is the same angle as the celestial equator. Now, these diurnal circles with regards to star positions are often called transits. An upper transit is when a star is crossing the upper meridian, meaning it's crossing the astronomical horizon above the horizon where we can observe it. A lower transit is just the opposite, when a star crosses the lower meridian below the horizon where we cannot observe it. Another important term to remember is circumpolar objects. They are objects that always stay above the horizon and appear to circle around the North Star Polaris. So they're called circumpolar because they circle the celestial pole. And so circumpolar constellations are ones that you are able to observe all year long and all night long because they won't set below the horizon. Probably one of the best examples of a circumpolar object is the Big Dipper. The Big Dipper will be observable all night long. Okay, and I've got another simulator that I want to show you guys that we can kind of helps us visualize the and so that kind of wraps up the celestial sphere. This diagram here kind of sums up all the main points of the celestial sphere. Zenith, always directly overhead. Nadir, always underfoot. The cardinal directions, north, east, south, and west around the horizon. We've got the NCP and the SCP. We've got the circumpolar objects, and we've got the celestial equator and the astronomical meridians.